So here is just a little chart. These are some of the numbers that you're going to be encountering throughout this chapter. So what I usually tell students is, again, the calculator will help you figure out whether you have a perfect square or a perfect cube or a perfect fifth power. I would recommend, though, at least knowing your perfect squares up to 12. Let me get my pen out here. Let's see. And I would recommend knowing, oh, let's just say all of your perfect cubes. There's only 10 of them. Okay. All right. And again, whenever you're in doubt, you can always use your calculator. All right. So, but if you happen to run into any of these numbers here, and to be honest with you, I don't really remember seeing much above sixth power. So we could probably even narrow it down to this. All right. Just use the calculator if you're in doubt. There's nothing wrong with that. All right. Let's see. Okay, now you may have noticed as we've been going through these examples that sometimes it's okay to have a negative number as part of the radicand, and sometimes it's not. And the difference is that if the index is even, the radicand must be non-negative for the root to be a real number. So for example, the fourth root of 81 is 3, but the fourth root of negative 81 is not a real number. However, if your index is odd, the radicand can be any real number. So you could do the cube root of 125 is 5, or the cube root of negative 125 is negative 5. All right, so the key is whether your index is odd or even. All right, so that brings us to finding the nth root of a to the n, where a is a real number. So here's a fun question that I want you to think about for a couple minutes. Pause the video, come back when you're ready. If x is a real number, does the square root of x squared always come out to just be x? So what I would recommend you do while you're trying to figure this out is use a good variety of values for x. All right, and I'm just going to leave it at that, a good variety of values. Okay. Okay, so if you look at just the left side of the screen, that has to do with the question I asked you. So if I pick a number, let's say 4. All right, and the question is, does the square root of x squared equal x? Well, if x is 4, then x squared is 4 squared, which is 16. And of course, the square root of 16 is 4. So for this particular number, the answer is yes. They do come out equal. But one number doesn't cut it. The question was, does the square root of x squared always equal x? So what I was hinting at a minute ago with a good variety of numbers, I meant like some that are positive and some that are negative. All right. So if we try negative 4, and again, here's where I have to be careful. The square root of x squared, when you square negative 4, that looks like this. You have to put those parentheses around the negative 4. The square of negative 4 is 16. The square root of 16 is 4. And guess what? This number and this number are not equal. So while this up here was a yes, this down here is a no. The question is always, the answer is no, not always. Now here's a question I didn't ask you, but I'm asking you now. All right. Do you think the cube root of x cubed always equals x. So why don't we go with those same examples? If we put in a 4, four cubed is 64. Let me just put a line here. And the cube root of 64 is 4. So the answer for 4 is yes. Okay, but one number doesn't cut it. So let's try -4. If I put a -4, here we have the cube root of blank cubed. I put a -4 in the blank. The cube of -4 is -64. -64. Oh, but the cube root of -64 is -4. So guess what? That's also a yes. Okay, now technically 2 numbers don't cut it either. All right, if we were all math majors, I would try to come up with a way to prove this. All right. But it happens that, yes, the cube root of x cubed does always equal x. So again, it comes down to that even or odd index thing. So let me show you what's going on. Back to the presentation. Okay, so here are the questions that we thought about. All right, so here's the rule. If your index is odd, if n is an odd positive integer, then the nth root of a to the n is just a. So what you can do is you can think of that nth root and that nth, I'm sorry, that I said that in the wrong order. The nth root and the nth power just kind of cancel each other out. You can think of it that way. However, if your index is even, as we saw when a was -4, what we got out as our answer was a 4. So the way to fix it is, instead of saying the nth root of a to the n is just a, if your index is even and you don't know anything about the number a, you don't know if it's positive or negative, then the best you can say is that the nth root of a to the n is the absolute value of a. So before we go into examples, I just want to tell you that this is something I am not going to drive you crazy with throughout the chapter. I'll never forget the very first year I was at Merced College and I taught Math C. I was teaching it out of a different book where they really drove everybody crazy with this. It was all over the place. And it is something that you have to pay attention to in calculus sometimes. And your calculus instructor will remind you of that if they're anything like me, all right? Most of the time, there is going to be something in the directions that says assume the variables are non-negative. And if the variables are non-negative, then we can just say that the nth root of a to the n is just a, and we don't have to worry about the absolute value. So what you want to be on the lookout for is something in the directions that says this: assume the variables represent any real number. That means it could be positive or negative. All right, so let me switch back to the tablet. So notice in this first example, the index is even. So there's just one thing that I want to do before I write down the answer for this. I want to make sure that this is written in the form nth root of a to the n. All right, in this problem, the only thing that's being raised to the power 4 is just the x. So what I'm going to do is I'm going to rewrite this as the 4th root of some whole thing to the power 4. That whole thing would be 2x, okay? And then 2x has kind of taken the place of my a in the rule. And so because the index is even, I would say that this is equal to the absolute value of 2x. You can also write it as 2 times the absolute value of x. Hopefully, your online homework will not care which way you write it. I would be very happy with either one of these. All right, I think the next one is in some ways simpler. Again, it has the form nth root of a to the n. It actually has the form square root of a squared. All right, so if we don't know anything about a, the best we can say about the square root of a squared is that it's the absolute value of a. So in this case, all I can say about the square root of the square of y minus 6 is that it is the absolute value of y minus 6. All right. One other thing I want to give you a heads up about, be very, very careful with those absolute values. Leave it just like that. The absolute value of y minus 6, see, I jinxed myself there. The absolute value of y minus 6 is not y plus 6. The absolute value does not change that minus to a plus. All right. So leave it just like this and forget I ever even said that. We're not even going to go there. All right. And then the last one, the 5th root of z to the 5th. So now we have an odd index. This is just going to be z. You would not include absolute values. It would actually be wrong to put an absolute value there. So make sure you don't put one. All right, I think we're finally almost done. There's just one more thing to look at, and that is graphing. Whoops. So remember, just recently we talked about the graph of f of x equals the square root of x. It looks like what you see here. So now I'd like to talk about the graph of f of x equals the cube root of x. So I've got that all set up on my tablet. So let's take a look at that. All right, so this time I've set it up like this. So if you can remember how we did our square root graph, we picked our values of x so that they would work nicely inside the square root. So now I want to pick numbers that work nicely inside a cube root. Okay, so what kinds of numbers would those be? They would be perfect cubes, numbers like 8. And you can even use -8. You can also use 1. You could use -1. And you can even use 0. All right, so those are all very nice numbers to use inside the cube root because they are perfect cubes. All right, so now if I just jot a little cube root here, this is what's going to give us our y values. The cube root of 8 is 2. The cube root of -8 is -2, right? The cube root of 1 is 1. Cube root of -1 is -1. And the cube root of 0, what number cubed gives you 0? Well, it would be 0. All right, so let me see. I picked this blank grid because I had a feeling we might be dealing with some bigger numbers. Maybe I could have gotten by with the one I usually use, but this will be okay. You know what? I'll make these spaced out a little more like that. Okay, so what points do we want? We want 8, 2, which is, let me let's see here. Okay, 8, 2, which is right about there. -8, -2, which is over here. 1, 1, which is right here. -1, -1, which is right there. And 0, 0, which is right here. All right, so I don't know exactly how to describe this cube root graph. Sort of like an S shape, maybe. Actually, on the right side, it looks very similar to your square root graph. The big difference is that there's also stuff on the left side because, again, you are allowed to take the cube root of a negative number. Just a couple of quick observations about this graph. The domain of this function, what kinds of numbers are you allowed to put in for x? Well, you can put in any numbers you want, positive, negative, doesn't matter. So the domain is all real numbers. And the range is also all real numbers, all right? Remember in the last chapter, we were talking about taking the graph and squashing it onto the y-axis. If you squash this graph onto the y-axis, you would hit the entire y-axis, all right? The graph does climb up very slowly, but it does keep climbing up, and that's what's important. All right, so the very last example, and I'm actually going to do this different from how I've always done it before. I can't even remember why I've usually done it this way. So the question is to identify the domain and then graph the function g of x equals the cube root of x plus 1. So you know what? Instead of using this table, I don't think that's the best way to do it. I am going to do this based on the graph we just drew. All right, so I will pick a different color, let's say blue, for g of x equals the cube root of x plus 1. All right, now think back to chapter 8. It hasn't been that long. And try to remember, what does the graph of g of x equals the cube root of x plus 1 have to do with the graph of f of x equals the cube root of x? In other words, I know we didn't talk about cube roots in chapter 8, but we did talk about what happens to a graph when you replace x with x plus 1. There's the bird saying hello in the background. What happens when you replace x with x plus 1 is that it shifts the entire graph 1 unit. Which way? 1 unit to the left. All right, so what I'm going to do is just take all of those points that I plotted earlier, and I'm going to shift them all 1 unit to the left. Okay, and what it's not perfect, all right, but what you're supposed to get out of this is that the graphs are identical except that one has been shifted 1 unit to the right. So it's going to end up looking something like this. What is the domain of this function? We said the domain of the other function was all real numbers. Well, the domain of this function is also going to be all real numbers. If you squash this graph onto the x-axis, you would hit the entire x-axis. Another way of looking at it is, what kinds of numbers can you put in for x? Well, you can add 1 to any kind of number you want, and then you can take the cube root of any kind of number you want. All right, so you can put any number you want into g of x, and you will get out a perfectly good real number. All right, not the shortest section we've ever done, but that's finally the end of section 10.1, and we will see you next time.